Have you ever gazed up at the clear night sky and wondered what lies hidden among the countless twinkling stars? Each of those bright specks doesn't just stand still. It spins on its own axis, much like a giant cosmic top twirling endlessly in the vast darkness. But did you know that's just the beginning? Because each of these stars also performs a mesmerizing rotational dance. They constantly move around an even grander entity, tracing invisible orbits that take millions of years to complete a single revolution. Just think, all these magnificent movements are happening right now. At the very moment you're breathing, you're blinking. It's a ceaseless cosmic dance, an eternal motion. And surely you've heard this before, haven't you? That our planet, Earth, is spinning. Yes, that's absolutely true. This isn't some new discovery. We all know that Earth completes a full rotation every single day. It's precisely because of this rotation that we witness the sunrise and sunset daily. A simple explanation, right? But let's pause for a moment. Did you know that our Earth doesn't merely spin on its own axis? It also undertakes a grand journey around the sun, completing one orbit each year. And even the sun, the center of our system, it's not standing still either. The sun is hurtling at incredible speed along a colossal orbit, revolving around the center of our Milky Way galaxy, a single revolution that takes a staggering 200 million years to complete. And not only that, our entire galaxy, it also spins, carrying billions of stars with it. All of them simultaneously revolve around a central core, much like horses galloping on a giant cosmic carousel. Now try pointing your telescope towards any distant galaxy. What will you see? Spiral shapes, of course. Always beautiful spirals, colossal swirling vortices of light endlessly rotating in the vast expanse of space. So let's temporarily leave the vast cosmos and look down at our own planet. Can you observe a storm gradually forming over the immense ocean? You'll see it swirling violently. Similarly, a terrifying tornado sweeping across a vast plain also spins relentlessly. Or even a tiny whirlpool forming on the surface of a river or lake. Everything spins. So here's the core question we need to answer. Why does everything, from the tiniest dust particles to the most colossal galaxies in the universe, constantly rotate? Have you ever wondered why this universe is filled with ceaseless rotational movements? Why doesn't everything simply move in a straight line from point A to point B, but instead keep spinning? And what's even stranger, if the moon constantly orbits the Earth revolves around the sun, and the sun itself is circling within the vast Milky Way, then why don't we witness any catastrophic collisions? How is it that such apparent chaos doesn't lead to a continuous chain of disastrous collisions? Perhaps you believe you've grasped the concept of orbits, haven't you? You're probably familiar with textbook illustrations, perfect circles, arrows indicating direction of movement, planets gliding along invisible tracks like trains on a fixed schedule. But do you truly understand the nature of what's happening? Let me reveal a truth that might make you reconsider. Our moon isn't peacefully and serenely suspended around Earth, as you might imagine. In reality, at this very moment, as you're reading these words, the moon is constantly plummeting straight towards our planet. Consider this. Earth's immense gravitational pull is relentlessly tugging at the moon, never letting go for a single second. A perpetual, never-resting force. So the question is, why doesn't the moon simply fall straight down on us? Why does it steadfastly remain high above, seemingly absolutely safe in the night sky? The answer, which might sound illogical at first, but listen carefully, the moon is actually falling, but at the same time it's also moving sideways, gliding through space at an astonishing speed of over 3,000 km/h. And this is the crux of it, an incredible feat of nature. While the moon is constantly falling towards our planet, the Earth's curved surface simultaneously curves away from it at an equivalent rate. To visualize this, imagine throwing a stone. The stone will trace a curve and then fall to the ground, right? Now imagine throwing that stone even harder. Its trajectory will become longer and appear flatter. Keep throwing it harder, faster. That curve will extend even further, increasingly so. And now imagine throwing it at an extraordinary, unbelievably fast speed, so much so that the stone's falling curve perfectly matches the natural curvature of the Earth. The stone will just keep falling and falling, but the ground continuously curves away from it. What's the result? It will never hit the ground. It will just keep falling forever, ceaselessly around the Earth. And that is the essence of an orbit, an endless fall, a journey that never reaches its final destination. And you know what? Our moon has been performing this exact dance for billions of years. It falls towards us, glides past Earth, continues to fly, circles the planet, and then begins a new cycle of falling. An eternal cycle of free fall and gliding through space, just falling, then gliding. And the result of this complex series of movements is the elegant circles we call orbits. The same holds true for the relationship between the Earth and the Sun. Our planet is constantly hurtling directly towards the Sun, pulled tightly by its immense gravitational force. However, at the same time, we are also moving sideways at a dizzying speed, exceeding 100,000 km/h. This extraordinary velocity is enough to create a nearly perfect circular orbit around the Sun. We don't fall into the Sun simply because we have no intention of landing on it. Did you know that not only our Earth, but all other planets in the solar system, from Mercury, Venus, Mars, to the giant Jupiter with its countless moons, or the magnificent Saturn with its spectacular ring system, along with even more distant planets, are all perpetually orbiting the Sun? Even distant planets like Uranus and Neptune are no exception. All of them are in a state of continuous freefall around the Sun. But how is it that they don't plunge directly into the Sun? It's the miraculous interaction between gravity and their sideways motion that has created these astonishingly stable orbits, enduring through billions of years of cosmic history. However, a core and challenging question arises. What is the origin of this sideways motion? Why did all objects already possess kinetic energy when gravity began to exert its influence? To unravel this mystery, we must turn back time to the very beginning of the universe. Imagine, our universe was born from a cataclysmic explosion. All the immense energy, once compressed into an infinitesimally small point, suddenly expanded violently and unstoppably. It was from that primordial energy source that matter began to form. This started with the appearance of subatomic particles, followed by the formation of the first atoms, primarily hydrogen, the most basic and simplest element in the periodic table. As the newly formed space continued to expand, these nascent atoms began to spread out, coalescing into colossal clouds. Try to imagine, these were gaseous structures of unimaginable size, stretching across such vast distances that light itself would take years to traverse them. But were these colossal primordial clouds entirely still? Absolutely not, because in this vast universe, nothing truly stands still. There were always disturbances, residual vibrations, creating constant motion. For instance, it could have been the powerful impulse from a nearby supernova explosion, pushing gas particles away. Or it could be the invisible pull from the gravitational force of a denser region of matter. Even extremely small temperature differences are enough to make gas masses move, creating shock waves that propagate throughout the vast universe. Even the tiniest quantum fluctuations in the fabric of space-time can create minute asymmetries. All these factors, whether large or small, contribute to the ceaseless motion. The result is a completely random, chaotic motion without any fixed direction. The giant gas cloud drifts along with each part of it moving in its own distinct direction. It's extremely important to remember this cloud is not a solid rock, but entirely a collection of diffuse gas. Therefore, each region within the cloud can move independently of the others. While some parts drift in one direction, others move in the opposite. Some parts rise, others sink. The entire cloud resembles a giant three-dimensional maelstrom, with movements that at first glance appear completely aimless. However, a pivotal event is about to unfold. It is at this moment that gravity begins to exert its influence. Regions within the cloud, which already had a slightly higher density of matter, now exert a stronger gravitational pull. This causes them to attract even more gas from their surroundings. As a result, they become increasingly denser, and so they continue to pull countless other gas particles inward. This is a relentless, self-reinforcing spiral. The giant cloud under the influence of gravity begins its own collapse. Initially, this process unfolds slowly, almost imperceptibly to the naked eye. But then, the rate of collapse accelerates dramatically. Gravity relentlessly pulls all matter inward, converging towards the center. And it is at this point of convergence that an incredibly fascinating and wondrous phenomenon is about to reveal itself. Have you ever wondered about the chaos within a giant gas cloud? Imagine each tiny particle of matter hurtling in a completely random direction. But what happens when that cloud begins to shrink in size? Surprisingly, those chaotic movements don't disappear. They remain intact within. Of course, a significant portion of these movements will automatically cancel each other out. Imagine, when a stream of gas moving left collides with a stream of gas moving right, they automatically nullify each other's effects. Similarly, rising gas will neutralize sinking gas. But do all movements completely vanish? No, not all movements are absolutely cancelled out. There's always a residual part left over, a net rotation, however small. Even if this rotation is almost imperceptible, even incredibly faint, it is certainly still present. So the entire cloud mass begins to rotate gently. To visualize this better, let's imagine a graceful ballet dancer or a figure skater performing an elegant pirouette. With her arms outstretched, she's spinning steadily. Then suddenly, she unexpectedly pulls her arms close to her body. What do you think happens next? Exactly. Her spin immediately accelerates incredibly. Now, she's spinning many times faster than before. The remarkable thing is no energy was added to the system. She didn't push herself to speed up. She simply brought her body mass closer to the axis of rotation. And then, completely automatically, inevitably, the speed of rotation dramatically increased. This miraculous phenomenon occurs thanks to a very fundamental law of physics, the law of conservation of angular momentum. This is considered one of the most crucial laws governing our entire universe. In the simplest terms, this law states that every rotating object will always continue to maintain its state of rotation. And if the mass of the rotating object is pulled closer to its center, its rotational speed must increase to ensure that angular momentum is absolutely conserved. This is not advice or a suggestion, but an immutable, unchangeable law of nature. And you know what? That collapsing gas cloud operates on precisely the same principle as a figure skater. As the cloud narrows and all its matter is compressed towards the center, any rotation, no matter how small, will be extraordinarily amplified. A seemingly insignificant drift suddenly transforms into a fierce, powerful spin. As a result, the cloud begins to spin faster and faster, accelerating rapidly as it continues to contract. And when the rotational speed reaches a certain threshold, another spectacular transformation begins to unfold. Can you guess what happens? The cloud starts to flatten out. All the matter that was previously dispersed freely in all directions is now compressed into a single two-dimensional plane. From a spherical mass, the cloud is now transformed into a disc-like structure. To visualize this better, think of a skilled pizza maker at work. He takes the dough, tosses it into the air, and spins it. What miraculous thing happens to that dough? Of course, it flattens out. The dough spreads, gradually forming a perfect round disc. It is this rotational force that pushes the material outwards. However, it's important to note that this spreading only occurs in the plane perpendicular to the axis of rotation. The final result is that the dough becomes flat and round. Have you ever wondered what governs the universe? The physics of every gas cloud adheres to an immutable law. Rotational force constantly pushes matter away from the axis in the equatorial plane while simultaneously compressing it vertically. And the ultimate inevitable result is a perfectly flat rotating disk. This is not a random coincidence at all, but a necessary consequence. This phenomenon doesn't just appear sporadically or in a few special situations. On the contrary, it is a continuous, ceaseless process. Indeed, every giant gas cloud in the universe, as it begins to collapse under its own gravity, transforms into a rotating disk. This is an irreversible physical destiny. This is clear evidence of how fundamental physical laws operate. The combination of collapse and an initial rotational motion, no matter how small, always leads to the formation of a disk structure. And what happens at the center of this disk? Invariably, gas and dust accumulate with increasing density. As matter continuously pours in, pressure skyrockets, pushing temperatures up to millions of degrees Celsius. Exactly 10 million degrees Celsius. Eventually, the core becomes so incredibly hot and dense that an extraordinary revolutionary phenomenon begins to occur. At that point, hydrogen nuclei begin to collide, fuse, and combine to form helium. This nuclear fusion process releases an enormous, unimaginable amount of energy. This is the moment nuclear fusion ignites, marking the birth of a star as it shines brightly for the very first time. And do you know what? This new star also rotates. This is inevitable. The star inherited all its rotational motion from the very giant gas cloud that formed it. In fact, there was no other option. The law of conservation of angular momentum absolutely ensured that this had to happen. So, what about our sun? Approximately 4.5 billion years ago, our own sun also formed through a similar process. A giant gas cloud located somewhere in the Milky Way began its destined collapse, spinning at an ever-increasing speed and gradually flattening into a colossal disk. The central part of this disk heated up relentlessly until nuclear fusion ignited. From that moment on, the sun has burned brightly and spun ceaselessly. Approximately every 25 days, it completes one rotation around its axis. However, did the disk of matter around the nascent star vanish as soon as the sun formed? Not at all. A vast amount of material remained, forming a colossal disk of gas and dust, which continued to orbit the young sun in the same direction, the original rotational direction of the parent gas cloud. This special disk of matter has a scientific name, the protoplanetary disk, and it was within this very disk that the planets began to form. If you're fascinated by these newly discovered insights into how the universe operates with such precision and elegance, we would greatly appreciate your support. These marvelous natural laws truly deserve to be widely shared. Over the next millions of years, countless tiny particles within this protoplanetary disk continuously collided with one another. What's astonishing is that during these seemingly gentle collisions, they began to connect at a microscopic level, each tiny dust particle stuck together, gradually forming larger particles. And so these larger particles continued to seek out and merge with others. This was a slow, step-by-step process, yet utterly unstoppable. Each tiny dust particle, each minuscule element, gradually combined to create larger objects. Dust turned into pebbles, and pebbles continued to accrete to form solid rocks. How could tiny pebbles become colossal mountains in space? Imagine this. Small rocks gradually grew into larger boulders, then transformed into mountain-like structures. These cosmic mountains, known as planetesimals, continuously collided and merged, laying the groundwork for much larger things. And what was the result of this relentless, gradual growth? After millions of years of continuous accretion, the planets we know today finally took shape. Do you want to uncover the fundamental secret behind the order of our solar system? Here's the crucial insight that illuminates everything. Each planet was already in motion long before it actually coalesced into a distinct celestial body. Consider this. The very particles that eventually formed our Earth were already orbiting the Sun. As these particles collided and merged, they remarkably retained their initial orbital momentum. So why do all the planets move in sync? This lateral motion was present from very early on, an unavoidable legacy inherited from the swirling disk from which they formed. Consequently, all 8 planets in our solar system orbit the Sun in precisely the same direction. Is this just a cosmic coincidence? Absolutely not. There's no random lottery in the universe. All these celestial bodies emerge from the same single rotating disk, thereby inheriting precisely the same rotational momentum and, more importantly, the same direction of rotation. Imagine this celestial parade. Mercury leads the way, followed by Venus, then Earth, Mars, the colossal Jupiter, ringed Saturn, and finally the distant giants Uranus and Neptune. Each planet moves in perfect alignment, adhering to the original flow of the very disk that birthed them. What if things were different? If planets had formed independently from separate cosmic clouds, their orbits would be utterly chaotic and unpredictable. Some might spin clockwise, others counterclockwise, all at different angles and planes. But fortunately, that's not the reality we observe. Instead of complete chaos, they coalesced from a single disk, and thus they all orbit the Sun together, much like harmonious records spinning on an old phonograph. Isn't that incredible? All the planets lie on the same plane and move in the same direction. Now, truly marvel at the astonishing flatness of these orbits. Have you ever wondered why all the planets orbit the Sun within just a few degrees of a single common plane? The answer is elegantly simple. They originated from a remarkably flat disk. To grasp this, consider the primordial disk. While it might have been a few million kilometers thick, its diameter stretched for billions of kilometers, making it incredibly flat. Since the planets formed within this astonishingly thin disk, their orbits inherently adhere to this initial striking flatness. Besides orbiting, there's another fascinating motion. Planets also rotate on their own axes. For instance, our Earth completes a full rotation approximately every 24 hours. How fast do other planets spin? Mars takes a similar amount of time for one rotation. However, giant Jupiter, despite its enormous size, completes a full rotation in only about 10 hours. What about Saturn? It takes about 11 hours. Clearly, each of these celestial bodies rotates on its own axis. So what drives this continuous rotation? The fundamental reason is exactly the same. As each planet grew, accumulating material from the surrounding disk, that incoming material inherently carried its own rotational momentum. Was there ever a perfect balance of forces? No, a flawless equilibrium was never achieved. Instead, there was always a net accumulating spin. And here's a powerful principle at work. The more mass a planet accumulated, the more pronounced this spin became, thanks to the conservation of angular momentum. Essentially, a larger planet means it spins faster. What happens once this rotation begins? Once initiated, this spin is relentless and ceaseless. Amazingly, it continues to rotate even billions of years later. Does this model extend beyond planets? Absolutely. Even moons follow this identical formation pattern. Once some planets reached a sufficient size, they, in turn, created their own smaller disks of material orbiting them. Have you ever wondered how moons form? We can envision them as miniature versions of the protoplanetary disk around the Sun. It was this very material orbiting the planets that constantly collided, accreted, grew, and eventually shaped into the natural satellites we know. Jupiter, with its dozens of moons, is a prime example. Saturn is no exception, possessing numerous satellites. What's remarkable is that they all follow a common rule, orbiting their parent planet. Is this a coincidence? Whether they are moons of Jupiter or Saturn, they all share a common characteristic, moving in specific orbits. And this is no accident, because all of them were formed from rotating disks of material. However, our moon has a somewhat different formation story. Nevertheless, the end result remains the same, a satellite orbiting its host planet. So what made that difference? According to the most widely accepted hypothesis, the moon's origin was a catastrophic collision. A massive object slammed into our young Earth. Can you imagine the immense destructive power? The tremendous force from the impact propelled a huge amount of material into space around Earth. This very material formed a glowing, vaporized disk of rock continuously orbiting our nascent planet. This is the evidence for the moon's formation. Gradually, over time, this disk of material cooled. The fragments continued to collide, coalescing, and from that, our moon was born. A dramatic process, wouldn't you say? Although the origins may differ, a common principle persists: rotation and formation from a disk of material. So if this principle holds true for moons, does it also apply to much grander structures? Let's expand our view to entire galaxies. Our Milky Way, a colossal spiral galaxy, is a powerful testament to this. It's an unimaginably vast rotating disk where hundreds of billions of stars constantly revolve around the galactic center. Can you visualize that immense scale? Our sun is located midway between the center and the edge of the Milky Way. To complete one orbit around the galactic core, it takes approximately 200 million years. A staggering number, isn't it? We are moving at an astonishing speed, about 800,000 kilometers per hour, along with billions of other stars in our vicinity, all revolving around the galactic center. But what makes this entire colossal galaxy spin ceaselessly? Why do galaxies rotate? The answer lies in the same principle that causes all other objects to rotate. Galaxies form from the collapse of a colossal gas cloud, a truly immense structure with a diameter of millions of light years. This is the evidence for the beginning of cosmic rotation. This primordial cloud already had a rotational motion, perhaps very slow, almost imperceptible. However, as it began to collapse under its own immense gravitational pull, that initial rotation, no matter how tiny, was amplified to an astonishing degree. Do you see the magic of physics? As a result, the cloud spun faster and faster, gradually flattening and transforming into a colossal disk. It was within this magnificent rotating disk that stars were formed and continued to orbit the galactic center for billions of years, a relentless process of creation. Not just the Milky Way, but other galaxies in the universe also exhibit this same incredible pattern. Most of them are spiral galaxies, colossal rotating disks of stars, all moving in harmonious coordination. Is this perhaps a universal law? However, not all are spiral galaxies. Some are elliptical, with amorphous structures and less order. But what's surprising is that even in these seemingly chaotic galaxies, rotational motion continues unabated. What does this tell us? The stars within them are constantly moving, orbiting the center, albeit on seemingly more chaotic paths. Nevertheless, one thing is certain, they are always rotating. This is undeniable proof of the prevalence of rotational motion. Rotation, quite literally, is present everywhere in the universe. Why? Because gravity is also everywhere. And here's the rule. Whenever gravity pulls things inward, whenever an object collapses under its own weight, any initial motion, no matter how tiny, will be extraordinarily amplified. This is a fundamental law of physics. Those tiny initial rotations will transform into colossal spins. Seemingly insignificant drifts will become furious vortices. This is an immutable law guaranteed by physics without any exceptions. It's truly astonishing, isn't it? And this is the core reason explaining why our universe has such clear structure, order, and shape. It's not merely a uniform cloud of gas spread throughout infinite space, but a dynamic universe full of laws. Do you understand the universe better now? Have you ever wondered what prevented the complete collapse of the universe? It's rotation. Objects don't just fall towards the center, they also move horizontally at the same time. It's thanks to this unique horizontal motion that direct collisions are prevented. Instead of crashing into each other, they begin to orbit objects, gradually forming vast disc-shaped structures. From primordial chaos, ordered structures emerged. Magnificent galaxies, brilliant stars, and familiar planets. All these wonders are the result of the complex interplay between gravity and rotation. Just imagine what would happen without rotation. Everything would simply collapse inward, causing giant gas clouds to condense into dense amorphous spheres. There would be no rotating disks of matter, nor any planets capable of stable orbits around stars. Instead of the ordered solar systems we know, the universe would just be chaotic masses of gas and giant stars. And perhaps there would be no stable enough environment for life to sprout and develop, no solid foundations, no worlds with solid surfaces like our Earth. Everything would become unstable and unpredictable. Therefore, our very existence is a powerful testament. We are here thanks to the universe's ceaseless rotation. Clearly, our existence is intertwined with this marvelous cosmic dance. But now, let's return to another intriguing question. What prevents collisions? Have you ever wondered why planets don't plunge directly into the sun? Or why the moon doesn't fall to Earth, even though gravity constantly pulls them closer? So, what's the secret behind preventing a catastrophic collision? The key answer lies in horizontal velocity, also known as orbital velocity, which we've mentioned before. An astonishing fact is that at the very moment you're reading these lines, the moon is actually falling towards Earth. Our planet's gravity constantly pulls it, but at the same time, the moon is also sliding horizontally at a dizzying speed, over 3,000 km/h. This speed is incredibly fast. As the moon hurtles towards Earth, our planet's curved surface simultaneously evades it at the same velocity. This means the moon continuously slips past Earth without ever touching it. That's why it maintains an orbit around Earth instead of falling straight down. Imagine this, if you drop an object from your hand, it falls vertically to the ground, simply because it has almost no horizontal motion. But what if you throw it sideways at the same time you let go? The object will trace a curved path, combining its fall with horizontal movement. This blend of the two types of motion is what creates the curved trajectory. And here's something interesting. The harder and faster you throw it, the longer and flatter that curve will be. Imagine you keep increasing the speed, throwing the object faster and faster. Eventually, if its falling curve perfectly matches the curvature of the Earth, what happens? The object won't fall down, instead it will start orbiting our planet. And that's the definition of an orbit. Our moon moves horizontally at an absolutely precise velocity, fast enough for its orbital curve to perfectly match the curvature of Earth's surface. This explains why the moon never gets too close, never collides, but simply orbits us forever. Just think, if the moon were to slow down even a little, it would immediately spiral towards us, getting closer and closer until a catastrophic collision occurred. However, the moon always maintains an absolutely precise velocity to stay in its orbit. The balance between its falling motion and horizontal motion is mathematically perfectly calculated. And did you know the same principle holds true for our Earth and the Sun? Right now, we are constantly falling towards the Sun, continuously pulled by its immense gravitational force. Did you know that even as we hurtle towards the Sun, we are still moving horizontally at a staggering speed of over 100,000 km/h? It's this extraordinary speed that makes the Sun's curved surface appear to recede from us at the same rate. Strange, isn't it? We are constantly missing our target, continuously circling the Sun instead of being pulled directly into it. So what would happen if our orbital speed slowed down? In that case, Earth would inevitably spiral directly into the Sun, with temperatures gradually rising until we completely incinerated. Conversely, what if Earth sped up? We would be flung out of orbit, flying straight into deep space, getting colder and colder until everything completely froze. But fortunately, we are at the perfect balance point, a wonderful harmony between falling and moving horizontally. This is the ideal condition for an orbit that is not only stable but also sustainable for billions of years. And what's astonishing is that this delicate balance isn't exclusive to Earth. It governs every planet, every moon, every satellite, and all celestial bodies orbiting another object in the universe. So how do they avoid collisions? Although they are all pulled down by gravity, they move horizontally fast enough never to crash into each other. Instead of self-destruction, they maintain a continuous dance around one another. What amazes us is how extraordinarily stable these orbits are, an unbelievable stability far exceeding all predictions. Just think, our Earth has diligently orbited the Sun for a full 4.5 billion years, always on the same orbit, maintaining the same average distance and at the same constant velocity. We have never once plunged directly into the fiery Sun, nor have we ever been flung into the cold, endless depths of interstellar space. Instead, we continue our cyclical journey, seemingly forever. Similarly, our moon has persistently orbited Earth for over 4 billion years, always steadfast on a single, unchanging orbit. However, there's an interesting fact. The moon is slowly drifting away from Earth, albeit at an extremely slow rate due to tidal forces. But don't worry, this is a very gradual process, almost negligible in a human lifetime. So what makes these orbits so fundamentally stable? What's the mystery behind their incredible persistence over billions of years? The reason they've remained virtually unchanged for billions of years lies in a simple yet powerful truth. There's nothing in space to impede their motion. Imagine this. Outer space is a vast expanse, a near-perfect vacuum. There's no air, no friction, and absolutely no drag. This means that once an object starts moving in the perfect vacuum of space, there are no factors to slow it down. Its motion will continue indefinitely without stopping. According to the laws of physics, energy and momentum are absolutely conserved. That's why these orbits simply persist forever. But look, here on Earth, everything eventually comes to a stop. That's because of friction and air resistance. These invisible forces constantly rub against surfaces, gradually converting kinetic energy into heat and ultimately bringing all motion to a halt. In stark contrast, in the vastness of space, there are no similar energy dissipation mechanisms. Thus, objects continue to move and orbit indefinitely unless they collide with something or are significantly acted upon by an external force. And that is the natural essence, the immutable law of the universe. Once an object begins to rotate, it will continue to spin ceaselessly into infinity. Have you ever wondered what keeps an object in orbit forever? Once an orbit is established, the object continuously revolves around it. This motion never stops on its own. It's a perpetual phenomenon. But did you know that right here on our planet, this same fundamental principle of rotation appears in much more familiar phenomena? Think about powerful swirling storms. What makes them spin relentlessly? The answer lies in Earth's own rotation. Our planet completes a full spin every day, a fundamental fact that shapes many natural phenomena. What's a direct consequence of this rotation? It's that different latitudes on Earth's surface don't move at the same speed. Notably, the equatorial region moves incredibly fast, at a velocity of about 1/600 kilometers per hour, Conversely, points near the poles move significantly slower. So what happens when air begins to move from one latitude to another? It has to cross a land surface that's rotating at inconsistent speeds. This difference in speed causes the airflow to deflect, its path to curve, and from there it begins to rotate. This powerful phenomenon is known as the Coriolis effect. And this is the scientific explanation for why storms in the northern hemisphere rotate counterclockwise, while in the southern hemisphere they spin clockwise. Clearly, Earth's rotation plays an extremely crucial role in shaping global weather patterns. So what immense energy source fuels a storm? The answer lies in warm ocean waters. As warm ocean water evaporates, it rises, forming a low-pressure area. This low-pressure zone, like a giant vacuum cleaner, draws in more air from its surroundings at extremely high velocities. Then this rapidly moving air current is affected by the Coriolis effect, causing it to begin spinning. This continuous rotation gradually forms a characteristic tight spiral structure. The continuous supply of additional heat energizes the system, making it increasingly powerful. As a result, this spiral structure spins at an ever-increasing dizzying speed. So what does a mature storm look like? It's a colossal swirling storm with winds that can exceed 160 kilometers per hour. Interestingly, terrifying tornadoes also form through a similar mechanism, just on a much smaller scale. Within large storms, powerful updrafts rise rapidly. But what makes them start to spin? When wind shear occurs, a sudden change in wind speed or direction with altitude, that rising column of air will begin to rotate. And as this column of air stretches vertically, a fundamental principle of physics comes into play, the law of conservation of angular momentum. According to this, the more the column stretches, the more incredibly its rotation speed accelerates. The result is a tornado, a violently rotating column of air with winds that can exceed 300 kilometers per hour, bringing immense destruction. You can even observe similar rotational motion in the most everyday phenomena, like water swirling down a drain in a sink. What's surprising is that even the slightest disturbance or asymmetry is enough to initiate this rotation. And once it begins, that rotation will sustain itself and even intensify as the water continues to swirl down the drain. So what is the fundamental principle behind all these phenomena? It's that rotation, once formed, tends to sustain itself and is reinforced by external factors. Is it possible that everything in the universe is spinning? The profound reason is that our universe originated from motion, and gravity skillfully transformed those initial motions into an ordered rotation. It has the ability to transform chaotic random fluctuations into perfectly organized rotating structures. It's astonishing how tiny initial movements can evolve into grand rotations. This cosmic pattern repeats itself at every scale imaginable, from the smallest particles to the most colossal structures. Look at the vast universe. Tiny gas clouds collapse under gravity, transforming into stars that spin on their own axes. Similarly, even larger gas clouds collapse, forming entire galaxies that are swirling through space. Have you ever wondered how planets are formed? In fact, the massive disks of material surrounding young stars are the birthplaces of the planetary systems that orbit them. What's astonishing is that the fundamental physical principle governing this process is entirely consistent no matter which case you examine. And the ultimate, inevitable result is always one: rotation. But did you know that this story of rotation began at the dawn of the universe, right from its very first moments? From its very beginning, the universe was never still. It possessed an intrinsic motion, ceaseless fluctuations, tiny differences in motion between different regions of space. Can you believe that those initial movements never stopped? It was relentless gravity that amplified those initial fluctuations. They were continuously reinforced, gradually organizing themselves into massive rotating structures, which are what shaped the universe we observe today. So, let's share in the comments. What aspect of the universe's rotation has truly astonished you the most? Is there anything you thought you understood clearly before, but now have a completely new perspective on? Take a moment to look up at the night sky. Do you realize that every twinkling speck you see, every single star, is constantly performing a rotational motion? Not only that, every planet orbiting those stars and even the most distant galaxies are spinning. All of this is intricately linked by a principle that is both simple and elegant: self-sustaining rotation. It was the collapse under gravity that powerfully amplified the rotational motion, and in turn, this rotation is a key factor in creating structure and order for the entire universe. Right now, you are standing on a planet that is constantly spinning, and this planet in turn orbits a star that is also rotating. That star in turn orbits a massive galaxy that is also spinning. And what's fascinating is that this galaxy itself was formed from material originating from colossal gas clouds, which were already rotating long ago. Rotation truly permeates every aspect of our existence, from the smallest microscopic particles to the vast cosmic scale. It's important to understand that there isn't some force actively making everything spin at this very moment. Instead, since its inception at the dawn of the universe, rotational motion has been unimpeded. Gravity amplified those tiny initial movements to an unimaginable degree, transforming microscopic shifts into colossal galactic swirls. It transformed initial chaotic movements into elegant, perfectly predictable circular orbits. Clearly, rotation is a fundamentally essential, indispensable element to the overall structure of the universe. From the tiniest whirlpool to the grandest spiral galaxy, we observe the same pattern, the same physical principle, the same law applied across all scales. This is one of the universe's greatest symmetries, one of the most profound characteristics shaping our physical reality. And hidden deep within it is a wondrous beauty, a mathematical elegance that is almost poetic. The universe, contrary to what many believe, is not a random mess, nor is it meaningless chaos. In reality, there is a clear order, recurring patterns, and immutable laws governing everything, from an apple falling to the ground to the majestic dance of entire galaxies. The same physical principle explains why the moon doesn't fall directly to Earth, and it also accounts for the characteristic spiral shape of galaxies. Did you know that the same law of conservation of angular momentum that helps a figure skater speed up when they pull their arms in is also the law that causes collapsing gas clouds to accelerate and form stars? We discover these cosmic laws not through mystical revelations, but through meticulous observation, rigorous experimentation, and precise mathematical deduction. The great physicist Feynman once stated, "Nature uses only the longest threads to weave her patterns, so that each small piece of the fabric reveals the structure of the whole." And he was absolutely right. The Earth's rotation is one of those crucial long threads. If you pull that thread, you will profoundly realize that everything in the universe is intricately connected. So the next time you look up at the moon in the night sky, remember this: it is falling ceaselessly, constantly, missing its target, and forever orbiting Earth in a gravitational dance. At this very moment you are breathing. Billions of other distant worlds are performing the same grand dance, obeying the same immutable laws, and participating in the same cosmic ballet that began billions of years ago and will continue for billions more. Why does the universe spin? Simply because it cannot stop. Have you ever wondered if there's any possibility beyond what physics has determined? It's astonishing that we sentient beings residing on a tiny, constantly spinning planet, orbiting an ordinary star within a galaxy also swirling among billions of others, possess the extraordinary privilege to unravel the origins of that truth. If you're passionate about the adventure of exploring the universe's rotational laws, hit subscribe to continue this journey with us. The universe still holds countless unveiled mysteries. Have we truly understood the full extent of its captivating operational mechanisms?